and then we'll kind of talk about how to do it. All right, so do we see that they gave us the interval that included the margin of error, right? So we don't need to find the interval. I mean, we do, but to come up with this interval won't be bad. We're going to do 0.15 minus 0.06 and 0.15 plus 0.06. So in terms of like, for these intervals, like coming up for this particular one, they gave you everything you need to know to calculate the interval relatively quickly. So as we look at what that is, we get 0.09 and 0.21. And the whole idea is we're trying to decide, do we have evidence to say it's not 20% like the program is supposed to do? Okay. So for part one of part A is asking, does this interval suggest that it's not 0.2? And so what do you guys think? No? Why not? Yeah, so you could say no. And the justify your answer will be 0.2 is in the interval. That's the quietest he's ever come in here. Does the interval suggest that it is 0.2? So oh, you guys, you know what? This is supposed to go here. Oh, man. I read it backwards. So the question, part one is asking, do we have evidence to say that it's not working? The answer is no, because 0.2, oh, that was right, because 0.2 is in the interval. So we can't say that it's not 0.2, but can we say that it is for sure 0.2? No, why not?
Because it's just the interval.
There are other values in that interval, right? The interval suggests it could be as low as 9% or as high as 21%. Does this component feel okay? Okay. You guys. Part B is one of the hardest parts of a free response question I've seen in a really long time. So I'm going to let you guys read it. And theoretically, a long time ago, like in December, we kind of talked about the reasoning process that'll get us here. but it's not something that I would expect you guys to be like, oh yeah, for sure. Okay, so let's kind of talk through what we know. We have p hat equals 0.15, which is the exact same p hat that we had up here, yeah? When the margin of error. So, like, if we think about this 0.06, that was equal to some z star times the square root of 0.15, 0.85 over n. Are we comfortable with that component of it? And the question is, what would happen to this answer if I had 4 times the sample size? Because the level of confidence is staying the same, right? Same confidence level, and we have the same p hat. So the only difference is going to be, so the question is, what goes here if now my new sample size was 4 times that n?
The same z-score as before.
Yeah, because it's the same confidence level, the z-score would stay the same. So the z-scores actually don't make a difference whatsoever in the margin of error in this particular case because they're the same z-score. Okay, same level of confidence. So really what's happening is numerically we just have a 4 in the bottom of this second standard deviation formula, right? What's going to be the result of putting a 4 right here in terms of my answer? Is my answer going to get bigger or smaller? Smaller, because I'm dividing by 4, right? But am I dividing by 4?
No, because it's a square.
Because it's under the square root sign. So guess what my new margin of error would be? .06 divided by that square root of 4. Can we kind of see that? Which is 0.03. Whatever you do to your sample size, you do the inverse square root to your standard deviation, which means you do the inverse square root to your margin of error. All right? All right. So now my interval would be 0.15 plus or minus 0.03, which would be 0.12 to 0.18. Now can we say the thing isn't working? Because 0.2 is not in this interval. If 20% is working, this interval says it's not working because there is no 20%. So here's what happens. As your sample size increases, the margin of error decreases, and vice versa. And it's inverse in that one is going up and one is going down by the square root of whatever factor you're multiplying by. So for example, taking your 4 times your sample size was 1/2 the margin of error. So So inverse, then you take the square root of it. Okay? We feeling okay? All right, let's talk about Parkinson's disease. Do you guys know what Parkinson's disease is? Not really? How many of you have heard of Parkinson's disease? But in terms of what it actually is, okay, so it's a degenerative neural disorder. Okay, so typical symptoms include you start to get shakes, like there's a medical word for it, and my mind. Yeah, you start to get tremors in your arms and legs, and so and it's tends to run in families. Okay, so can you think of a reason why we might want to be able to smell if somebody has Parkinson's disease? So earlier diagnosis, which means earlier care, because it's related to genetics. I'm not sure it's preventable, but you can start doing like physical therapy and stuff to help manage the symptoms. Yeah, but certainly maybe an earlier diagnosis, so earlier treatment, stuff like that. And I think there are some like new medications that they're starting to develop and whatnot. Okay, so next I'm going to show you a quick video. Those of you at home, I'm going to email you the link to the video as well. How many she got right? Or how many she smelled to begin with, okay? So 19 out of 20 might convince us. Would anybody be convinced with less than 19 out of 20? 14 out of 15 would still convince you? What about 5 out of 6? No? No? Raise your hand if 5 out of 6 convinces you. 6 out of 7? Notice that if 5 out of 6 convinced somebody, then 6 out of 7 would also convince them, right? Okay. 7 out of 8? Perfect. 8 out of 9? 9 out of 10? 10 out of 11? 11 out of 12? 19 out of 20. So you're like 19 out of 20. All right. Can we start by agreeing that we should have some sort of standard that we use to make this decision? Or like we hope statisticians have some sort of standard they use to make this decision. Okay? And right now, what we need to do is learn about how do we make this decision. Okay? All right. So let's go ahead and say that the number she actually got correct was 11 out of 12. Okay? All right. Now, if she was just guessing on 12 shirts, how many would you expect her to guess correct?
6.
Why 6?
Because it's half. It's a 50% chance she'll get it right.
So if she's guessing has Parkinson's or does not have Parkinson's, it's 2 equal options, right? Theoretically. Okay. So because we assume her probability of correct is equal to 0.5, that would be she's just guessing, right? And we have a sample size of 12, we would expect 6. And but Joy did pretty well, right? She did better than getting 6 correct. Is everybody with me? Okay. So there are 2 ways we could explain how she got 11 out of 12 correct. Instead of, which was way more than the 6 out of 12 we expected. Can somebody tell me one of the explanations?
She can't actually smell it.
She can smell Parkinson's. I'm going to write this one over here, though. And what would that say about her probability of success if she can smell Parkinson's?
It's 0.92.
Well, that's what 11 out of 12 suggests.
Oh.
But are you with me that it would suggest that she's doing better than just guessing? Cool? Wait a minute. What's the other explanation? She can't. But was lucky. What would that mean about her actual success rate?
It's equal to or less than 0.5.
Really, if she's just guessing, it's 50% still, right? Okay. All right. And from looking around, just now we asked, feels like some of you are convinced at 11 out of 12 correct, and some of you are not convinced at 11 out of 12 correct, right? So how do we decide? Well, when we come up with our 2 possible explanations, this could happen in lots of different ways. So, for example, it happened a while ago. There was a lawsuit against Subway. I actually think it's in your Unit 7 notes. A lawsuit against Subway a few years back that was, they call them footlong subs, but they're not actually footlong. You with me? And so what happened is they went, an interest group who was like ready to sue Subway went out and took a random sample of footlong subs. They went to different restaurants around the country, stuff like that, okay? And they actually measured their sample. Is everybody with me? And the mean of that sample was less than 12 inches. Let's say it was 11.78 inches. Okay? You guys with me? There's 2 explanations for why the mean of the sample was less than 12 inches. One of those is, you guys tell me. How can you explain a sample of footlong subs being less than 12 inches? Yes?
It's a bad sample, or they just actually aren't.
Samples are not perfect.
So could it be just like, if they're actually a foot long, we're still going to get some that are less than a foot long and some that are more. So it could just be the nature of sampling makes this happen, right? And the other explanation is Subway's cheating. Before you ask me the results of this suit, I believe it was settled out of court. Everybody good? Okay, so we have a lucky or a chance hypothesis, and we have an alternative to chance being the explanation. Okay, so this is the chance hypothesis. Which in the statistics world we call the null hypothesis. Is anybody in AP Bio? Okay. Mr. Rummer will teach you the wrong way to do this. When you do these. And we note that null hypothesis with an H and a subscript O, meaning empty, null. So it's technically H0, not HO, but whatever. Okay? And then we have the alternative hypothesis. If we can rule out chance, the alternative is true. And we write that as the alternative, H sub A. So here's what we do. If we want to decide, can Joy smell Parkinson's? What we want to ask ourselves is, could 11 out of 12 happen by chance? Now, we've spent some time with probability. Could it happen by chance? Is it possible? Yeah. Just because something's possible doesn't mean it's going to happen. You know what I'm saying? Right? I mean, it's possible that I could develop the leg muscles to slam dunk a basketball, but that would require a 4-foot vertical when you consider my 5-foot frame plus about a 1-foot arm above my head, right? 4-foot vertical for someone 5 foot tall would be pretty impressive, right? In fact, impossible. I think it might be physically impossible. But like, you guys would be shocked if I slam dunked a basketball, right? Right? That would be very, very surprising to you. Okay. But what about if Biscuit did it? Can you?
Not yet.
Is there anybody on the team right now that can?
Michael.
Greer? Mm-hmm. Okay. All right. So, or, would you be shocked if Belk could do it? Lion? That one wouldn't shock me at all. I bet he can. Yeah. Okay. So, anything can happen by chance. So, what we do is we use probability to make our decisions. So could it happen? Sure. But if it's unlikely, that's what makes us start to be like, oh, okay. So, you guys, what we want to ask ourselves is, what is the probability that she gets 11 out of 12 right if she's just guessing? Everybody good? Well, let's think that through. We had n equals 12. We want to find the probability that x is 11. Or if she got 12 out of 12 right by just guessing, that would be more evidence, right? So essentially, we want to ask ourselves, what's the probability she could have got 11 or 12 right by just guessing? And man, we have the probability, if she's just guessing, we know, like, we're going to assume she's just guessing and just say, could this happen? This is starting to look a lot like some other questions we've done this year, doesn't it? And is this a binomial setting? Do you guys see how this is a binomial setting? So we could throw this into our calculators using, the binom CDF, right? And what does the CDF give us? It gives us the probability x is less than or equal to. So we got to rewrite this. What does x have to be less than or equal to? Because x is our number of successes, yeah? Are you guys with me? Which outcomes are not greater than or equal to 10 to 11? Anything below 11, which is less than or equal to 10. And then we find the probability x is less than or equal to 10, then we subtract from 1. Do you guys remember doing this? It's been a while. What are we getting?
0.003.
0.003. So you guys, if she's just guessing, the probability she gets less, or she gets 11 or more right, is less than 1%. So could it happen that she gets 11 out of 12 right by chance? Could it happen? Yeah. But I don't know about you guys. If something has a 0.3% chance of happening and it happens, I'm going to assume that something else is wrong. Yeah? Okay? So this probability is very convincing to me. And here's what it convinces me of. She cannot. She's not just guessing, because it couldn't have happened if she was just guessing. So now I can eliminate this as an explanation to how she got 11 out of 12 right. And if I eliminate this explanation, how many explanations do I have left? This is the only one. Is everybody with me? Okay. So, if the actual sample is unlikely when the null hypothesis is true, okay, we're going to do something. We're going to reject that null hypothesis. Okay? This should not have happened if she was just guessing. So I'm going to reject the idea that she was just guessing, which means I get to say she's doing better than just guessing. The alternative hypothesis is what is true. Okay? And if that's the case, so what happens then is, what if I can't reject? What if she would have gotten 8 out of 12 correct? Can we all agree that 8 out of 12 would not convince us? Because the likelihood that she gets 8 out of 12 right by just guessing is relatively high. Does that mean I can say she can't smell Parkinson's? She's still doing better than just guessing. It's just not enough to convince us that it couldn't be chance. So this idea of should we ever conclude that null hypothesis, we will never in our life conclude the null hypothesis despite what Mr. Remmer tries to teach us.
So like on the AP Bio.
On the AP Bio test, you might in fact conclude the alternative hypothesis or conclude the null hypothesis.
But on the AP Stats.
On the AP Stats test, we're not going to. Ever. We're never going to say the null hypothesis is true in AP Stat. It's not Mr. Romer's fault that the College Board makes him teach things the wrong way. And he shows a different approach, and we will learn that test.